Hi folks, we're going to take a look at an example of solving a rational inequality. Okay, so this is, I would say, one of the easier ones because the inequality is already set up that you've got 0 on one side of the equation, and on the other side of the equation you have one single rational expression, in other words, one fraction. Okay, and the next examples will take a look at where there's a little more algebra to do before you get to this point. Okay, but once you get to this point, we use the principle that the only place where a rational expression or a rational function can change its sign is at an x-intercept or at a vertical asymptote. Okay, another possibility could be a hole, but I don't think we're going to have that issue with this example here. Okay, so in other words, we have to find these zeros and the vertical asymptotes of this rational function. Okay, if we think of this on the left as being a rational function. So we do that by factoring. So let's try to factor this expression here. So I see a cubic at the top, and please, before you go and run to the factor theorem, please check if there's any traditional methods, and anytime you see a cubic with 4 terms, you should be thinking about using grouping. So let's do that here, see if it works. So if I factor out an x squared from the first 2 terms, I end up with x plus 4. Okay, now I need to create an x plus 4 here, and I'll get that by factoring out a minus 1, and I'm left with x plus 4. Okay, so grouping will work. And here, x squared minus 4 is a difference of squares, so x plus 2, x minus 2. Okay. So now here, let's continue. So x plus 4 times x squared minus 1. We're left with a 1 there. And we see that we can do even some more factoring because we've got another difference of squares up there. So x plus 4, x plus 1, x minus 1, x plus 2, x minus 2. Okay. Once I have everything factored out, I can now start deciding where this expression on the left is going to be less than or equal to 0. So as we said, the whole principle here is that the only place it can change sign is at an x-intercept, which we'll get from the numerator, or a vertical asymptote, which we'll get from the denominator. So all we have to do is test one point in each of the intervals created by the points we just talked about, and from there we can determine where it's less than or equal to 0. Okay, so I'm going to set up my number line here, and I'm going to start from left to right. So negative 4 is my leftmost concern. Now as I'm doing this, I notice that at the x value where the function equals 0, I'm going to include that x value in my solution because it's less than or equal to 0. So negative 4 makes the whole thing equal to 0. So I'm going to represent that by a closed circle. Okay, but as I go to the next one, negative 2, okay, that represents a vertical asymptote. So the function's not defined at negative 2. So at negative 2, I'm going to right away put in an open circle to remind myself not to include it in my solution. Okay, next we've got negative 1, which is a 0, so I do include negative 1, so close circle. My next point is positive 1, makes the thing 0, so I am going to include it. And the last important x value is x equals 2, but that is a vertical asymptote at that x value, so I don't include it in my answer set. Okay, so now, as we said, these are the only places where this expression can change sign. So all I have to do is check one value in any one of these intervals. If it's positive, it means it's going to be positive everywhere in that interval. If it's negative, it has to be negative everywhere in that interval because there's no place for it to change sign in between. Okay, so all I need to do is pick one value in every interval. So here let me pick the easiest value, less than negative 4. So I'll pick negative 5. Okay, so let's stick negative 5 into each of these terms. So negative 5 plus 4, that's a negative number. Okay, here negative 5 plus 1, that's another negative number. Negative 5 minus 1, another negative number. And the denominator, negative 5 plus 2, negative, negative 5 minus 2, negative. So let's see what the end result is here. Numerator has 3 negatives, so 3 negatives multiplied to each other gives me negative over 2 negatives gives me positive. Negative over positive, so in this interval the function has to be negative. And now I'm just going to repeat this process for each of these intervals. So here let's pick something between negative 4 and negative 2. Let's pick negative 3. Okay, negative 3 plus 4, positive. Negative 3 plus 1, negative. Negative 3 minus 1, negative. Over negative 3 plus 2, negative. Negative 3 minus 2, negative. So here we see that I've got a positive number in the numerator, a positive number in the denominator. So when I divide them, it's going to give me a positive number. Notice how I don't care what the value is. The only thing I'm interested in is the sign. Okay, so let's keep doing this. Let's maybe go a little faster. So negative 1.5. Okay, negative 1.5 plus 4, that's positive. Negative 1.5 plus 1, that's negative. Okay, negative 1.5 minus 1, negative. In the denominator, negative 1.5 plus 2 is going to be positive. Negative 1.5 minus 2, negative. So here we have a positive in the numerator, but a negative in the denominator. So the end result, a negative number. Here, let's pick 0. So positive, positive, negative. Okay, positive, positive, negative means I'm going to have negative in the numerator. And here, 0 plus 2, positive, 0 minus 2, negative. So I'm going to have a negative in the denominator. Negative over negative, positive. Let's pick 1.5 here, between 1 and 2. Positive, positive, positive. Positive in the numerator, positive, but 1.5 minus 2 is negative. So positive divided by negative, automatically negative. And now let's pick x equals 3 for our last interval. Positive, positive, positive. Positive, positive. So when I divide, positive number. Okay, so I just had to test one value in each interval to know the sign in the whole interval. So now I'm ready to give my answer. So x is an element of the set. Well, less than or equal to 0. So I need to include this interval here from negative infinity to negative 4. And because I do want to include when it's equal to 0, I use a square bracket to include negative 4. Okay, now union, the next time it's negative is in this interval here, from negative 2 to negative 1. I don't want to include negative 2 because that's where I have a vertical asymptote, so it's not part of the domain, but I do want to include negative 1 because that makes it equal to 0. Okay, and the final interval in which it's negative is between 1 and 2. And here I want to include 1, square bracket, but I don't want to include 2, round bracket. Okay, and there's my solution set. Okay, so just to recap, okay, once you have a rational inequality where you've got a single fraction less than or greater than or equal to 0, okay, you factor to determine the zeros and the locations of the vertical asymptotes. You create a number line with all those numbers, and you have to test one point, the sign of the expression at one point in every interval. Okay, that's it for now.